All right, so we're continuing looking at trig by looking at vectors in a plane. And we're going to spend a few days here talking about vectors in 2 dimensions. And the first thing that we need to do is understand what a vector is. And really there are 2 things. One is the vector and one is a scalar. These are 2 different related things, the vector and the scalar. A scalar is simply a measurement. It's a number. If we're talking about speed or a number of pounds or newtons if you're in metric, of force. If we're talking about a distance, he traveled 5 miles. Okay. He was driving 35 miles an hour. He was pushing with 200 pounds of force or of pressure. Okay? A vector, on the other hand, is a little bit more than that. Okay? It's a little bit more, and I'll let a friend of ours define this for us.
Oh, I haven't seen.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
All right, so that actually, believe it or not, is a proper definition of a vector, okay? A vector, it's something that has magnitude and direction, okay? Magnitude would be like the scalar involved, okay? There is a specific speed that we're going, but a vector will also give that speed a direction, okay? We could be driving 35 miles per hour, a scalar, but if I say that I'm driving 35 miles per hour going north, now I've given you a vector. Okay? If I say someone's pushing with 200 pounds of force, that's a scalar. But if I say he's pushing with 200 pounds of force against a wall, all right, and we can see the wall so we can see the direction that he's going, there, now we have a vector, okay? I could say that someone traveled for 10 miles, but again, if that's just a scalar, unless I tell you which direction he traveled. If I say he traveled 10 miles east from where he started, now I've given you a magnitude and a direction, so now we're talking about a displacement, okay? And that's a vector. All right, so these are 3 common vectors. Believe it or not, you've dealt with displacements a lot, okay? Anytime we were dealing with those problems that had to do with the bearings, okay? This one was so far away, and at this bearing, a bearing of 72 degrees or whatever it was, we had a displacement vector that you were being given. Okay, we didn't call it that yet, but that's really what you were working with. Okay, so we have scalars and we have vectors. So one thing that's going to be important is that you pay attention to what you're being asked for. Okay, and it's also going to be important that you are careful with your terminology. Okay, don't speed and velocity are ones that are really, really easily messed up, okay? If you are asked to give a velocity, you need 2 parts to your response. you need a speed, but you also need to tell which direction that speed is going. Okay? So, couple things just to make sure that we understand the difference here. Alright? Now, notation. There's some notation here involved that you may be unfamiliar with. And you'll notice here we have this lowercase letter v, and it has this little kind of half arrow above it. Okay? And here we have a vector over here, and we could call this vector v. Okay? There is a less commonly used notation that has the tilde above it instead of the arrow. I've only seen it really in one spot, but just so that you're aware. Another way that you'll see a vector denoted when you're dealing with things that are in print is they'll use a bold font. Okay? Now I don't want you, alright, I'm making a vector, okay? So I made it bold, okay? You can't hand print bold, all right? So you just put the little arrow above it anytime you're writing it, okay? So there we have vector v. We can also use notation that shows what our starting point is and what point we're going towards, okay? So here we have vector AB. This is the vector from A to B. Now, it's important here that you put the letters in the correct order. What's going to happen if I reverse the order of those letters?
That'd be in a different direction.
The arrow would be to be that.
Yeah, the arrow would be going from B to A. It's going to be the opposite direction. Okay? It's going to be the opposite direction. So, be careful here that you put your letters in the correct order. Okay? Now, another element here that we need to consider, we said that a vector has magnitude. Magnitude, we use this notation here. It looks like the absolute value symbol. Sometimes to avoid confusion, we'll use the double, like you see here on the right, the double vertical lines. Either way, that's talking about the magnitude of vector v. Okay? And it's important you understand this notation because you're not going to be asked in words necessarily what's the magnitude. You're just going to be given the notation here, and you're expected to understand what that means and what they're looking for.
It's like v, like vector v, like the standard way you address a vector.
It's a common variable that we use for the vectors. Kind of like we commonly use x in solving equations. With vectors, we commonly use v. A lot of times we'll use u, v, and w. So, alright, same thing, same notation applies with magnitude when we're talking about the magnitude of a vector going from one point to another. Now, you'll notice here, I'm talking about going from one point to another or something like that, okay? And that's most easily seen when we're talking about a displacement. But the reason why vectors are so useful is because it does help us visualize and compare things that we can't normally see, all right? I can't really see speed or velocity. Okay, we can see an object moving, and by that we're able to kind of judge speed, judge what their velocity is. But by drawing it as a vector, we can then look at and get a visual representation of that. And then we can also look at multiple velocities working together and see what a result of that would be. And we'll look at that here in the near future. Okay? Now, something that we'll get to and we'll talk about even more later on, but component vectors. Okay? Component vectors are vectors that give a horizontal and a vertical component rather than just giving you a magnitude and direction. Okay? I could tell you that we are traveling at a rate of 5 miles per hour at a bearing of 53 degrees. Okay? Or I could break that into horizontal and vertical components. I could say I'm going 4 miles an hour towards the east and 3 miles an hour towards the north, and combined those two velocities, the horizontal and the vertical components of the velocity, would give us the same thing as if I said we were going 5 units at an angle of 53.1 degrees. Okay? So here is horizontal component 4, vertical component 3. That gives us the same thing as if I said it was 5 at an angle of, or a bearing here of 53.1 degrees. Okay? That would be this angle right here. Okay? So this would be giving it as an explicit magnitude and direction. If I said 4 over and 3 up, that would be giving it as a component vector. And there's a couple of different ways that we could denote this. Alright? And really, all of these are used often, so you should be familiar with all of them. Okay? I could write this vector as what looks like a point. Okay? So in this case, it would be 4, 3. I could write it in parentheses like this.
Welcome back.
Oh, thanks. As 4, 3 this way. Okay. I could write it. Oh, let's move up here so let me write. I could write it like this as vector AB. A lot of times people will prefer one of these two middle ones to avoid it looking like a point, because that's another issue when we're dealing with vectors, is it's very easy to mistake a point for a vector or a vector for a point. So that first notation, while it is really common to see it this way, sometimes can be confusing. Alright? Or you'll also see it written as A times this vector I plus B times this vector J. But we'll talk about that. That's what's known as unit vector notation. All of those have their purpose. There are different purposes, different contexts where using it might be helpful. Okay, but okay, but all of those are talking about this same vector. And right now, all I really want you to get is the notation. Be familiar with the notation. We're going to talk about component vectors more specifically tomorrow. Okay? But today, what I want to look at is dealing with these more in a visual sense, okay? And looking at the concepts as well. What are these concepts telling us? First of all, the magnitude of a vector, that notation that we saw, magnitude of vector V, is represented visually by how long it is, okay? When you are making a drawing, or what we call a vector diagram, if you're making a vector diagram and you have one vector who has a magnitude of 10 and another vector that has a magnitude of 5, you should make the one that has a magnitude of 10 about twice as long as the one that has a magnitude of 5. Okay? Now, I'm not saying that you have to get out a ruler and measure it, but you should make it, approximately to scale. Okay? The more you do that, the easier it is going to be for you to see the relationships and be able to figure out the problems that you're going to need to be able to figure out. Okay? Now, that length, that measurement here, is what indicates the speed of our velocity vector, the pounds of force in our force vector, the distance that an object was displaced. Okay? So as I'm looking at, here are 3 vectors over here, okay? This one's a little bit shorter than this one is, okay? So this one would be the smallest magnitude, this one's a little bit bigger. This one up here, though, is clearly the longest, so that would have the greatest magnitude, okay? Now, another thing that you may have already thought of here, if we have these components, horizontal and vertical components, we can think in terms of direction by considering slope. Okay? Think about our vector v. If I have a vector v, we already said A and B are the horizontal and vertical components. So what that means is, for vector v, I'm going to go horizontally whatever A is, and vertically whatever B is. So what would I say the slope of vector v would be?
B over A.
Yeah, B over A. Okay? We can say that the slope is B over A. Okay? So, that's another relationship here. Some other terms. I know we're hitting a lot of terms today, a lot of different things, but we're trying to lay the groundwork for everything else that we're going to do with vectors here. Okay? Another term here related to direction is parallel vectors. Now, here's something that's kind of interesting about this is that you can have parallel vectors. Okay? You can have parallel vectors and actually not be going the same direction. Okay? You can have parallel vectors. They are vectors that are going to go either the same direction, like this one and this one, or they could go opposite directions. Okay? In which case, if I were looking at these in terms of angles, what would be true about the angle of this one and the angle of the one?
They're 180 degrees apart.
Yeah, they're 180 degrees different. Okay? It's going exactly the opposite direction. So they're still not going to intersect if we were to, put them next to each other. They're not going to intersect. They're opposite directions. Okay? So parallel vectors have the same direction or opposite directions. All right. Any questions so far? I know we're hitting a lot of different terms here we're going to have to keep track of. All right. One other one here. We have equivalent vectors. Vectors that have the same direction and magnitude. Okay? The same direction and magnitude. We're not saying equal here because they're not necessarily the same vector. We could have a vector u and a vector v, okay? But as long as those two vectors are going the same direction with the same magnitude, we would call them equivalent, okay? Now, I wanted to illustrate this. There's a simple illustration here dealing with force, okay? Here we have two people that are trying to pull this big box. So they have this rope tied to the box, and they're both pulling, all right?
Wait,
So
how is that rope tied to the box?
I don't know. I'm a terrible artist. All right, it's connected somehow here. All right, so they're pulling on this, and they are of equal strength, so they're working together, which means they're pulling in the same direction. Okay? They're pulling in the same direction, directly away from the box. Okay? And since they have the same amount of strength, they're pulling with the same magnitude or the same amount of force. So these two are equivalent vectors. Okay? Now we have another case though where we may not be working together. Okay? If we're not working together, that's kind of like a tug of war. Okay? Here we have the two people. Now they're pulling against each other. All right? And here this guy still has that same amount of force. He's pulling this direction. This guy, though, is pulling the opposite direction. Notice how I indicated the opposite direction with a negative. Okay? A negative in front of a vector simply means it goes the opposite direction. It does not change its magnitude at all. Okay? So since these two guys were equally strong, what's going to happen if they're pulling against each other?
Not gonna move.
They're going to cancel each other out, and it's not going to move. All right, we've got a tie here. Okay? So does that make sense? Make sense?
Yes.
Okay? All right, so that's the idea. Notice these would be parallel vectors. Okay? These are also parallel vectors. Equivalent vectors are always going to be parallel vectors. Okay? But here, same magnitudes, opposite directions. Opposite directions are going to be parallel. Okay? Yes?
Can like magnitude change, or is it always constant?
When you're talking about a vector within a situation,
Yeah.
it's going to be the same.
So it's like at like a certain point in time.
Yeah, yeah. And what you would have, like you're kind of thinking maybe like with something that has a changing velocity or something like that. Yeah, what you would have to do, I mean, you could have. It's going to be constant unless you're introducing different variables. For example, if you have what are known as parametric equations, you can express, and we'll look at these later. Actually, you can express a component of a vector in terms of time. That's what parametric equations do. And they'll say, okay, x is changing at this rate, you know, or at this function of time. Okay? So it is possible for them to change if you have some other variable involved. If I'm just talking about vector u is just vector u. So once you have the vector, its magnitude is set. Okay. Sometimes what you'll have, like especially if you're talking about, say, a projectile, where gravity is going to change your vertical component, because it's going to slow it down until it starts moving it back down to the ground. We'll talk about the initial velocity vector. we start with a velocity of this at this much speed at this angle, and then gravity is going to change things. Okay, we will look at those though later. All right, so I want to finish off today looking at graphically how do we do different operations with vectors. Okay, I want to talk about how do we do addition, how do we multiply a vector. Okay, so here we have two vectors. We have the vector u and the vector v. And first of all, for vector addition, what we would do is we would take vector u, okay, and we would draw it first, okay, and then vector v is going to be added onto it, okay. So you can see here I have vector u and then I have vector v. Now, think about vector addition as though you're following directions. Do u first and then v, okay? If I want to drive to my friend's house, very rarely could I ever drive just in a straight line to my friend's house, right? However, what I could do is I could follow this street first, and then maybe I follow this street next, and then I turn onto this street, and then I have this street here. And what ends up happening is I get from my starting point to the desired endpoint, but I had to add a few vectors together, okay? And that's really what vector addition is. It's looking at the result of different vectors working together, okay? Now watch this. So here I'm talking about traveling, all right? But check this out. If I had, let's go back to a box, and I had a number of different forces acting on this box. Let's say I had one force that was pulling straight up on the box, and another force that was pulling over this direction on the box, and another force that was pulling this direction on the box, and then another one that was pulling this direction but with not as much magnitude. You know how I can model what's going to happen to that? What the resulting force on that box is going to be? I would do it with vector addition. Okay? There's one. Oh, didn't quite get the angle right there. Okay? There's another one. There's another one. And there's another one. So what's going to happen to this box? The resulting vector is going to be this. Okay? So the box is going to be pulled that direction with this magnitude, whatever that is. Okay? And we can use trig and various other strategies to find out exactly what that magnitude and direction are. Okay? When we're talking about a resultant vector, we're saying if we have more than one vector acting on an object, what's going to end up happening? Okay? In other words, this is what you're actually going to see take place. Okay? So again, let's think about two people pulling on something. All right? If we have this and one person is pulling this direction here, another person is pulling this direction here, to see what's going to happen as a result, I can add those vectors together, and this, u plus v, is what's actually going to happen. Okay? Is everyone understanding this? It's really kind of a cool concept once you get your head wrapped around the idea. Okay? And you can do this with movement, the displacement vectors. You can do it with force vectors. You can do it with velocity vectors. Okay, let's say you're in a boat and you're trying to paddle your way straight across the stream. Okay, you're trying to go straight across a river, but the river is flowing at v direction and magnitude. So where is your boat going to go? It's not going to go straight across. It's going to get pushed by the water, and it's going to follow this path here, the u plus v. Okay? A lot of different applications here of what can happen. Okay? So that's vector addition. When you're given two vectors, okay, or more than two vectors, let's say we had, let's avoid u. Here's vector A, vector B, vector C, and vector D. This whole result is A plus B plus C plus D. Okay? So, there you have it. That's our vector addition graphically, or geometrically, we could say. Another thing I want to look at is scalar multiplication. This is a real easy one, okay? This is a real easy one to deal with. Let's say I had 3u, okay? Well, if I have 3u, let's come back up here and get 3u, okay? What do you think I'm going to do with these 3u's to get 3 times u? Add them, right? 3u is the same thing as u plus u plus u. Okay? Scalar multiplication means we are multiplying a vector by that scalar 3. Okay? So to do that graphically, I draw a u, and then I put another u after it, and I put another u after it. Okay? So describe for me what my result is. What happens here?
It triples in length.
It triples in length, and length represents what in a vector?
Magnitude.
The magnitude, okay? So in this case, our magnitude is tripled. What happens to our direction?
Stays the same.
It stays the same, okay? Our direction is going to stay the same, but our magnitude is going to be multiplied. Okay? So, this is how we can do scalar multiplication. And when you're dealing with one of these things, remember, you can multiply by a fraction as well. One thing that we're going to look at later are unit vectors. What do you think the magnitude of a unit vector is?
1.
1. Okay? So let's say u had a magnitude of 5 to begin with. How could I make the vector have a magnitude of 1?
Divide by 5.
Okay?
So multiply by 1/5.
And multiply by 1/5. Technically, there's no division by a scalar. So yeah, we multiply by 1/5. Same thing. Okay? So we'll do that later on here, but this idea of scalar multiplication is really a simple concept. Remember, the direction will stay the same, the magnitude will be multiplied, and you can multiply by a fraction, a decimal, it doesn't matter. You can multiply by any real number. Okay? So, that's the concept, the terminology, the notation related to vectors, some of our basic ideas here and how vectors are related to each other, and then also just some beginning vector operations, okay? So I've given you a little bit of practice to do, okay? Show that u equals v. Try to get those, we talked about the horizontal and vertical components, okay? Just doing some basic things with those, all right? Here, you're asked to sketch Alright? So, draw U and V, and then try to sketch. What would negative V look like?
If you air like this.
Okay? And then do these other operations as well. Try to draw them to scale the best you can. Okay? Another application of that, same idea. And then this one gets you thinking. There's a lot of different vectors here. Let me ask you something though. How do I get, if B is going to the left, how do I get to go to the right instead? Negative B. Alright? So keep that in mind as you're doing these, okay? And they're asking you true or false. Now notice how are vectors equivalent? They have the same magnitude and direction, right?
Yep.
Do they have to be in the same location?
No.
No. Vectors are not bound to a location. Alright? So don't just say, well, A is over here and D is over here, so 97 is automatically false. No. Think about what is the magnitude and direction. Okay? R, the magnitude, and direction the same. Okay? Alright, so not terribly difficult stuff for your practice, but it's important that you get this stuff down right from the get-go. Okay? So take some time and work on those.